Hey guys, today we're going to start learning some calculus, and we're going to start with something called a limit. So, first thing we're going to look at is this picture. So this is a graph of our rational parent function, or 1 over x. And before, when we were talking about asymptotes, we actually did this a lot when we said as x goes to infinity, what's y doing? So as x is getting bigger and bigger and bigger, we can also see that y is getting smaller and smaller and smaller and approaching that asymptote at 0. Now, there's a new notation for that, and that's called a limit. It's the same concept, but we write it like this. So this is pronounced, or whatever said, the limit as x approaches infinity of the function equals to some y value. So this is telling you where x is going, and then your answer is going to be a y value. And the same idea, as x gets bigger and bigger and bigger, y is going to 0. So these two notations are the same. It's just this one is a little bit more compact. So we can also find limits for numbers. And so this one says the limit as x approaches 1 of my function. And so what I'm going to look at is I'm going to see where is this function going. So if I'm approaching from the right side going to 1, I see that I would be right here at 1, at y equals 1. If I go look on my left side, I can see that I'm also approaching that value of y equals 1. So my limit with that number would just be 1. Okay? And so this happened to be that the value of the function was the same thing as the limit right there, but that doesn't always happen. But that's something that's really easy to do if your function is defined in that place. So the formal definition of a limit is right here. If f of x becomes arbitrarily close to a single number L as it approaches C from either side, the left side and the right side, then the limit of f of x as x approaches C is L. And that's just this notation. So they're saying if you're getting close to a number, if that number exists, you would have this limit as x goes to some value. So C is just a value, it's a number, and L would also be a number. Sometimes it could be, if we're not looking at a graph, it could be a little expression. Okay, so let's look at some examples. The first one says the limit as x approaches 1 of x squared plus 3. Now I could draw a picture if I really wanted to, because this would be my function right here, and I could look and see where x is going. But the easiest thing to do, and the thing that you should always try to do, is plug in this c value. So plug in 1. Because if something happens there, then that would be your answer. If you have a number there, then that's just what your graph would be approaching. So if I do 1 squared plus 3, that's 1 plus 3, or just 4. So that was pretty easy. All we had to do was plug in that value. Of course, it's never that easy, so let's look at example 2. If I go ahead and I plug in -1 into this function, because that's what I'm always going to try to do, I'm going to have -1 plus 1 in the top, and I'm going to have -1 squared minus -1, which would give me a plus, minus 2. So I have 0, and then I would have 1 plus 1 minus 2, which also gives me 0. Now, if you get something that says 0 over 0, that's bad news bears, and this is what's called the indeterminate form. So indeterminate doesn't mean that the limit doesn't exist. It just means that I need to change something about my equation to see if I can see what's going on in the function. So if you get 0 over 0, that doesn't mean stop and say does not exist. That means that you're going to stop and see if there's anything I can do to change my equation. So if I look on this guy, this is a rational function. My top is x plus 1, and I could factor this bottom part into x minus 2 and x plus 1. So if you notice right there, when we did rational functions, we would have that these guys would cancel. And so, if you remember when we had our rational functions, if I had a factor that canceled out, that was a whole. And that, if you remember, we also called that a removable discontinuity. Continuity, such a long word. Okay, so if you have a factor that cancels, you're going to have a hole there. And so what we would normally have done then to graph this function is then just look at the remaining part, or 1 over x minus 2. Now if I go ahead and I try to find the limit as x approaches -1 on this function, that's really okay for me to plug in a -1. I would have 1 over -1 minus 2, which would just get me -1/3. And if you remember that when I plug that number back in, that was how I found my hole. So your graph is getting really, really close to that point. It's just never going to actually equal it. So that's going to be how you find a limit if it's an indeterminate equation. Okay, so it doesn't equal that point, but it approaches that point. Okay, now that was with no picture. Here is another thing that we're going to have to know how to do, is looking at a picture of a piecewise function. So this is why we needed to remember what a piecewise function was. So if I look, and I'm looking for the limit as x approaches -2, I just go ahead and I look at my graph. And so this is going to be your x value, and I'm going to look at it from both sides to make sure that they're the same. So as it's going from the right side, my function is approaching 0. As I go from the left side, my function is also approaching 0, and that value actually exists, so it would just be like plugging the number into my equation, and I would get that that limit is 0. So the y value as x approaches -2 is 0. Now if I look at some of these other funky parts that's going on here, the limit as x goes to -1. So if I look and I want to figure out where is x going to as x gets, or sorry, y going to as x gets to -1, I'm going to again look at it from both sides. So as I approach from the right side, as I'm coming in from this direction, I can see that my graph is approaching +2. But as I see if my graph is approaching from the left side up here, I'm approaching a different value. I'm approaching that hole, and that is at 1. And so in order for me to have a limit that exists, they have to be the same on either side. So since the left side and the right side don't equal each other, we get to say that the limit DNE does not exist. Because when I look here, there's a break, there's a jump in the graph. So if I look at something like -3 though, again, I'm going to go look from the left side to the right side. I'm going to erase this stuff. And if I am coming in from the left side on my function, I'll start over here, I see that I'm getting really close to -1. There's a hole there, but I'm going to get really close to that number. And then if I'm coming in from the right side, I'm also going to have that value of -1. So I actually do have a limit here. It's at -1. Now if they asked you though to find the value of f of -3, the value of the function, I have to look for that filled in circle. So since there's an open circle here, my actual value of my function there would be +1. And that can happen. That's okay. We still have a limit that exists because my graph is getting closer and closer to that point. It doesn't have to actually equal it. Okay, the function value doesn't have to equal. And so we saw this does not exist. And you can now quote Mean Girls, the limit does not exist when these three things. These are the three cases that we can have when a limit does not exist. So we saw some of them before. And the first one is that if the left and the right side approach two different values. So that was like the one we just saw in the piecewise where it had that jump in the graph. And so if you wanted to think about that as a break or a jump, that would be correct. So the limit's not going to exist if you have a break or a jump in your graph. The second way that it's not going to exist is if you have an unbounded graph. And basically, all that means is that you have an asymptote. It's getting really, 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 really big. Or really, 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 really small. So if I looked at this graph, the limit is x goes to 0 of 1 over x. If I graphed this, I would see I had this rational function. And as I was going to 0, from the left or the right side, it's getting close to infinity. So that's getting really big. It has an asymptote, but the other direction, it's going down towards negative infinity. So that's an unbounded graph. That's not going to exist there because of the fact that they're approaching two different values and they're really, really big. And the last case, if a limit does not exist, is if you have something called an oscillating function. And this is actually easier to see on the calculator for this particular one. So I'm going to open it up. And I have this wonderful looking thing. It's sine of 1 over x. And I'm trying to see what happens as it gets closer and closer to 0. So if I just look at the regular graph, it's going to graph really slow just because, you know, there's something interesting going on in there. So I'm going to go zoom in and see what happens. So if I look here, I can see that my graph Oh, there it goes. You can see it down there. It's graphing faster in that window. It's doing this funky thing where it's going up and down. And it's really interesting to me. If you keep zooming in, what happens? So I'm really small right now, and see how many times it's like bouncing around right in the 0. And if I looked in my window right now, it's super duper small. It's at negative 0.625, and it's bouncing around that much. So an oscillating function, you're not going to see it super duper often, but it's something that's doing really weird stuff as it approaches that number. So something like sine wouldn't be an oscillating function because it actually is approaching some number, but this guy, this sine of 1 over x, does, I did a box apparently, and so it's just going to start bouncing around, and so that's another example of when that function is not going to exist. So now you can quote Mean Girls with confidence, because the limit does not exist in those 3 cases. I will see you tomorrow.